You're familiar with these graphs in the Python physiology book. We will reach to color cycle. From the skeletal muscle physiology, you have learned two types of muscle contraction, isometric and isotonic. Can you remember?
Yes.
Which part of cardiac muscle contraction is isotonic and which one is isometric? Do we have both muscle contraction in the heart?
No.
So, explain. We do not have both?
No,
Are you sure?
I'm not sure.
Okay then. So, which type do you think we have in the heart? Isometric or isotonic? Isotonic means you have muscle length change. Isometric means the length is fixed but the force is changed. See,
I think isometric.
this is isometric, this is isotonic force contraction, means the muscle length is changed. Take a look. But this is isotonic. The muscle length doesn't change, but the force inside it.
It's also isotonic.
It's
Which part is isotonic in
the muscle contracts. It gets
Which part?
just ventricles.
No, both in ventricle and atrial we have the same situation. In which phases we have isometric contraction, in which phase we have isotonic? We have both in the muscle. During isometric, isovolumetric contraction, the length doesn't change.
Yes.
The pressure inside is increased, but the volume doesn't change.
Yes.
This is isometric contraction. What about the ejection? The contraction, see, when the pressure inside the heart passes from the 80, the valves are open. The contraction is still continuous because the pressure inside the ventricle will go up onto 120. So this part, when the volume doesn't change, but the pressure increases, is called isometric contraction. But during ejection, we have isotonic contraction. We have both. So, if you can remember from skeletal muscle physiology, if you want to study the characteristic of contraction itself, we use isometric contraction. Means if you take out a gastrocnemius muscle from the frog, fix it in one end, and attach it to a force transducer, and apply a stimulation to the belly of the muscle, you will have isometric contraction. And if you connect the panel base to one end and force transducer to the other end, and if you stimulate the belly, then the muscle will have isotonic contraction and lifts the weights. This is called isotonic. So, in muscle contraction, you should apply a tension to the muscle itself before it contracts. This tension before contraction is called preload. If you do not apply a preload, the muscle will not contract. The preload in the heart is equivalent to venous return. The preload is venous return. Those panel base, the force the muscle should overcome is called afterload. Afterload in skeletal muscle equivalents to panel base. Here in cardiac muscle physiology, which is called afterload. Here, in cardiac muscle physiology, afterload is intra-aortic pressure, or blood pressure, or systolic blood pressure, or peripheral vascular resistance. So, preload equals to tension before contraction. In the heart, it is equivalent to
Venous.
venous return or end-diastolic pressure. And afterload equals to
Intraventricular.
aortic pressure, systolic aortic pressure,
Or blood
peripheral vascular resistance, or
blood pressure.
no, systolic pressure. End-diastolic pressure and end-systolic pressure. End-diastolic volume or end-systolic volume, all are the same. So preload and afterload.
The preload happens when you don't put tension.
If you do not apply any tension, I mean if you don't push two ends of thread, you put two threads, one to the one tendon, the other one to the other tendon. Fix it with a pin and the other one to the force transducer. If you apply a stimulus to the belly of the muscle, then the muscle will not
Contract.
respond even if you do not put a pretension before applying the stimulation. This pretension is called preload. Here in the heart, this preload equals to venous return. Venous return. Afterload is the panel base. Or in the heart, it is systolic blood pressure. Amen. So this is called preload. We have discussed sympathetic and parasympathetic phase, Frank-Starling law. Now, I want to discuss the effects of hyperkalemia and hypercalcemia on the heart. Can you guess what is the effect of hyperkalemia? The normal extracellular potassium concentration is 3.5 up to 5 millimole per liter. If we increase, we have learned it in cell physiology. If we increase the extracellular concentration of potassium up to 8 millimole per liter. If we increase extracellular potassium concentration, tell me what will be happen. The normal is 3.5 up to 5 millimole per liter, or milli-equivalent per liter of extracellular fluid.
Arrhythmia.
So what kind of arrhythmia? Can you remember Nernst equation?
No.
From cell physiology, Nernst equation. Goldman-Hodgkin-Cox equation. I have discussed it here. Anyone see what is the Nernst equation? Let me explain it, and then you can guess. This is Nernst equation. If the membrane is permeable to just to one ion, for example potassium, then the membrane potential will be minus 61. If I increase the extracellular fluid concentration of potassium, then what is happening to this fraction? Is it bigger or smaller? It will be smaller. Then the fraction will be
Well,
less negative.
yes.
It will be less negative. For example, suppose that the membrane potential is minus 90 millimole. If I increase extracellular fluid potassium concentration, then the membrane potential will be
Increased.
will be.
Increased.
Less
Yeah, because there is a lot. It's gonna
See?
be opposite.
If I increase the denominator, the fraction will be
Small.
Small.
decreased, smaller. And this
Less,
figure will be,
less negative.
means it will
negative.
bring
Yeah.
minus 60 for
Less
example.
negative, that's means
Less negative
increase.
means,
Increase.
no.
The less
I
negative,
got it,
that's
right.
means increase.
See, this is this negativity means intracellular is more negative than extracellular. It doesn't mean.
It's
You
just
see,
direction, right?
The negative sign implies that the intracellular part is negative than.
This
It
is
doesn't mean that it is bigger than this.
This is
one.
reciprocal.
Bigger. This is in mathematics what you call it?
Absolute value.
Absolute value, exactly. Absolute value.
Is this
It doesn't mean that you are right. Mathematically, you are right. This minus 60 is bigger than minus 90, but this is an absolute value. Means
I wasn't know that
the
it's
cell
direction.
membrane is less negative. When the cell membrane is less negative, means it is depolarized.
So
It depolarized.
trachycardia would happen.
Hmm?
Trachycardia would happen.
No, listen to me. Listen to me. Means if I increase the extracellular fluoride potassium concentration, the less will be less negative and depolarized.
In which case it's increase the
If you add more potassium to the plasma or to the serum.
if I put potassium.
Yes.
Uh,
See what is happening. At which membrane potential sodium channels will be open?
Then-
Threshold
Minus 65.
Minus 65.
In normal cardiacs, ventricular and atrial, and minus 45 in nodal cells. Listen, if you increase potassium, extracellular potassium fluoride concentration, the cell membrane resting potential passes that minus 65. When the cell membrane passes that minus 65, then the sodium channel inactivating gates will be inactivated and will not respond anymore. The cell will be depolarized, but passes from the threshold of opening of H gates. And the cell will not respond. Based on Nernst equation, the cell will be depolarized, less negative. But since the inactivating gates will not respond after minus 65, then the cell will not respond. This is an antiarrhythmic. Property of potassium ion.
so
And
it's
the heart will stop when it is flaccid during diastole.
it's gonna to stop the rhythmic of the heart.
The same will be happening
Uh,
in SA and AB note 2. Yes. The cell, the heart will be flaccid and stop during diastole. This is hyperkalemia effect on heart. Hyperkalemia and hypocalcemia both have the same effect. In hypercalcemia, if we increase the calcium, extracellular calcium, then the heart will stop at systole when it is contracting. This is a spastic contraction. That would be flaccid relaxation when you have increased extracellular potassium. But if you increase extracellular calcium, the heart will stop during systole. in contracting state. So hyperkalemia and hypocalcemia have the same effect. Hypokalemia and hypercalcemia both have the same result. Did you get it? It is mentioned in guideline physiology book.
Hypocalcemia.
Hypocalcemia and hyperkalemia.
Hyperkalemia with
Increasing potassium with decreasing calcium both have the same effect. Decreasing potassium and increasing calcium have the same. Decreasing potassium, increasing calcium, and also the increasing body temperature. If you increase body temperature, first cardiac output will be increased. The heart rate will also be increased because ion channels will be more permeable to ions during hyperkalemia. But after some time, proteins will be denaturated. And then we will have bradycardia. First we will have tachycardia. Cardiac output will be increased, but then cardiac output and the heart rhythm will be decreased. If you increase the blood pressure, there is a trend in the book. If you increase it up to 160, then cardiac output doesn't change. But from that on, cardiac output will be decreased. First mentioned. And now let me explain the stroke work output and stroke. Up to here you have 4 phases. If you want to measure the external work output, this curve is called volume pressure curve. If you want to measure the external work output, you should measure area under the curve of pressure volume. Curve. Pressure volume. 120, 50, 120. This is milliliter. This is millimeter of mercury. Am I right? Pressure, volume, pressure curve. If you want the amount of work that is done by the heart during each beat, the heart performs work. What is the formula of work? Work is equals to the amount of work for each beat. This is called a stroke work output. If we want to measure the stroke work output for the heart, we should measure the area under the curve of volume pressure. We have 2 types of work. What is the work? The amount of energy, the amount of energy that is used to move blood from the low pressure vein to high pressure arteries. This is one type of work. The other type of work in the heart is to accelerate blood. We accelerate blood to its high velocity pressure. This is another. So we have 2 types of work in the heart. Moving blood from the low pressure vein to high pressure arteries. Accelerate the blood to its high pressure value. This is kinetic work, and the other one is external work. So, the energy that is converted into work to the total energy that is used is called efficiency of the work of the heart. Part of the energy that is converted into work to the whole energy is called efficiency. The efficiency of the heart is 20 up to 25%. It is just like the other motors in physics we have. Most of the energy in the heart is coming from fatty acids. Is coming from fatty acids. 70 up to 90% of the total energy is coming from fatty acids, which combines with oxygen in oxidative phosphorylative method of using energy. Fatty acids combine with oxygen in mitochondria to produce energy. 70 up to 90% of the total energy is coming from fatty acid. The rest, 10 up to 30, coming from glucose and lactate. Fatty acid I mentioned. 70 up to 90 from fatty acid. 10 to 30 from glucose and lactate in the presence of oxygen. So, if you can calculate the amount of oxygen that the heart is used, the amount of oxygen that the heart is used, you can calculate the amount of work that the heart is done. Because 90% of the work, of the energy that is used, is coming from oxidative phosphorylation in the presence of oxygen.
So I will be able to calculate just 90% from the, the heart.
The amount of oxygen that the heart is used is very near to the amount of energy that is used, because 90%,
Yeah, but still there is like different.
10%.
Yes.
Very small. So, practically, in order to measure, because calculating the work is very difficult, but calculating the oxygen that the heart is used is very easy. You can take a blood sample from the arterial system and from the central venous system. The oxygen that is present and the oxygen that is taken up from the heart. So it is very easy to measure the oxygen that is used by the heart itself. So you can easily find the amount of work that is done by the heart. So you have a time and tension. So my question is that, which part of the cardiac cycle uses more oxygen? How many phases do we have?
5.
During a cardiac cycle, a systole and diastole. Which part? Which one? You see, don't tell me systole. You have 3 phases. Filling, isovolumetric contraction, ejection, isovolumetric relaxation. This is a cardiac cycle.
Contraction.
Which part uses more oxygen?
Isovolumetric
Are you
contraction.
sure? No, I'm not sure.
Yes.
Yes.
Which part uses more oxygen? See?
No,
Relaxation.
Listen.
Isovolumetric.
Isovolumetric contraction. See? The heart to
Needs more.
reach the blood pressure to 80, then when the valves are open, no need. So, listen. Isovolumetric contraction uses more energy than those 3 phases. So we have time, see, listen, we have time, tension. Which part of the cardiac phase uses more tension? Isovolumetric contraction. Based on Laplace law, listen, in an spherical shape, like the heart. Suppose that heart is a sphere. In a spherical shape, just like heart. Tension equals to pressure times radius over 2. Tension. So we have tension time index. Tension means the amount of oxygen that is used by the heart. The more tension, the more oxygen that is used. The greater the oxygen, the greater the tension, the more oxygen that is needed. So, in an spherical, this is Laplace law. In an spherical shape, tension equals to pressure inside times radius. One of you asked me a question. This is the answer. See, we have two types of hypertrophy. Eccentric hypertrophy and concentric hypertrophy. Concentric and eccentric. Suppose that we have a stenotic aortic valve, and the heart, the left ventricle wants to push the blood from a small diameter opening. See what is happening. Gradually, the wall of the left ventricle will be added more actin and myosin in the wall. See, this is called a concentric hypertrophy.
It's also more thicker than the.
Listen to me and then answer the question. See, parallelly, actin and myosin, more sarcomere added to the wall. What is happening to the diameter of the left ventricle? That will be a smaller. This is called concentric hypertrophy. So if you reduce, see, this is an adaptive response. If the cavity is reduced, the wall is thickened, and the cavity is reduced, what is happening to the tension?
Increases or should
Reducing.
it?
The radius is reduced. What about the tension?
Reduces.
The tension will also be reduced. This is an adaptive response. This is called concentric hypertrophy. During hypertension, a stenotic valve. But see what is happening? During eccentric hypertrophy. Volume overload. The first case is pressure overload. But the second type is called volume overload. Volume overload expands the internal cavity. The radius increases. The tension will also be increased. The amount of oxygen will be increased because it is directly proportional to the amount of oxygen that is used. And the failure will be more deteriorated. This is called time tension index.
So which is more dangerous, the concentric or eccentric?
Eccentric. This is called dilated cardiomyopathy. Dilated. Because you have bigger radius. Bigger radius equals to more wall tension. More wall tension means more oxygen. More oxygen means more failure. Question? Plus 2. What is the time? 12:30. Go and have a lunch and then we will be back here. 1 is good.
1:30.
At 1. No, because I want to cover all the. If you read these parts, forget about you can understand based on what is mentioned. See? If I explain it to you, then you can easily learn. Otherwise, I will just like a skeleton or physiology. You cannot cover all the questions.
Is it enough to just study the slides?
Slides plus the book. Because in the slide, it doesn't mention any discussion. Read the book thoroughly and plus the slides. I will give you the slide.
Could we focus more on what you said?
Yes, why not? Yes, sure. Because most of the discussion I brought you in the classroom doesn't thoroughly in the book. That is why I put more pressure on them, especially for example. See, law plus law doesn't mention in the text. It is mentioned, bring the book, it is mentioned that here in this part, the book just mentioned see here. This is the explanation here. Here, TPR. It doesn't mention concentric, eccentric, but here at the end, it is
Page
mentioned that
123. اشتراك العراق.
see, the amount of chemical energy required for a given amount of work output is greater than normal, even though the heart is already failing. This is, the heart is failing, meaning it doesn't work properly. But the amount of energy that is used is more than when the heart is
عندي
working,
PDF copy.
effectively.
PDF copy.
So, this is eccentric, it doesn't mention here. When the heart is dilated, eccentric hypertrophy means volume overload. Concentric means pressure load.
Are these mentioned in burn and bloody? Eccentric and concentric?
Even in the Guyton physiology book, in cardiac failure, there is a cardiac failure, heart failure section. In that section, I'm sure that it is mentioned. Yes, in burn and bloody. Any question?
No.
You can have a rest and then relax.